we mentioned the wave has a quantity k here. Okay, again we use k. K is very common in physics. This is probably the third time we meet k, right? The first time we meet k is kinetic energy. The second time we meet k, it's a spring constant. Now it's also appeared in wave. Okay. K is related to an important quantity called the wavelength. Okay, you probably heard about the wavelength many times when we talk about all kinds of wave. But do you know what I mean by the wavelength? The wavelength is this kind of characterization. If you have a wave, it's oscillating like this way. Okay. Another wave, say, like this way, okay. So, either like this kind of big wave, or some smaller wave, like this, okay, not a crowd wave, okay. So, you can see from one peak to another peak, you have some distance for different wave. For this one is this large, okay. This distance is called the wavelength. So it measures the distance between one peak or another peak. Of course, you can also measure it from one valley to another valley, or one center point to another center point. Similar, okay, they will give you the same wavelength. So this is called wavelength. Now, wavelength is related to k. We can write the equation between the k and the wavelength as k equals to 2 pi over lambda. Okay? If you compare this, there's some similarity in this equation, but they are talking about different quantities. K equals to 2 pi over lambda. So K is the reciprocal of the wavelength multiplied by a constant, 2 pi. Okay, so it's proportional to the reciprocal of the wavelength. So physically, you can understand this K like this. First, we understand the wavelength. A small wavelength means crowded peaks, right? Like that. A large wavelength means far distance between these kind of peaks. So increasing wave, lambda, that means your wave will be from like this to this and this. Okay? Less crowded peaks in the same distance. And since K is proportional to the reciprocal of the lambda, so that means K increase in this direction, right? Okay. So large K actually means crowded wave like that. Small k means this kind of wave. Okay? That's the physical meaning of the k. And k has a special name. I always forget what's the name. Okay? So we always say k. What's the name of it? Angular wave number. Okay? Because that's quite, this is very, seems a meaningless name, so I cannot remember it. Okay? It's called the angular wave number. Okay. Now, I want to make some comparison between k and omega. So here, let's look at omega equals to 2 pi over t. K equals to 2 pi over lambda. And omega these two quantities measures how the waves or the oscillation of each point repeated in time. The repeated pattern as a function of time. Okay. This quantity k and lambda, they also measure the repeated pattern, but it measures the repeated pattern along x direction. So the special repeated pattern. Okay. So basically, wave omega and t, they describe this factor. Am I going to make a fast-moving wave or slow-moving wave, right? But on the other hand, can you see, we can also make difference in terms of the spatial pattern. Okay? So I can make crowded wave. I can also make less crowded wave, right? So they are talking about the repeating pattern for the time or for the distance. Okay. So, but they have some similar relationship like that. And if you look at the graph here, I'm plotting the wave, okay, for a particular time. And then the wavelength lambda is the distance between peak and peak. But please note this graph and this graph. If this is time, this is y, this is y. This is time t. This is position x. So this graph, if we plot it for the wave, it will be a graph of the oscillation and for a particular position. Position x. And this graph is the wave, graph of the wave for a particular time t. Okay? And they will look similar to each other. Harmonic function. But this, so if I measure this distance, what's that? In this graph, what's the distance between the peak to the peak?
Yeah, wavelength.
Wavelength?
Phase.
Phase?
And
It's okay, so we measure it along time axis. So it must be something has a meaning of time. Okay. In all these quantities we are talking about, which one has a meaning of time? No, frequency is not time. Who has the unit of second?
Hertz.
No, hertz is not. Hertz is 1/2 Which quantity has the meaning of time? Period, right? This is period. Okay, we talked about this before when we look at the graph of the oscillation. This is the oscillation graph. And what's the meaning here? This is wavelength. Wavelength is something in meter. Okay? Length is called wavelength. It's some length. Period is the time for one cycle. Is some kind of time. So along time axis, you are going to measure the period. Along x-axis, you are going to measure the lambda. But the same thing here is that, what's this? What do we call this distance? Amplitude ym, and this is also amplitude ym, because they both use the same y-axis, the distance measured from the oscillation. Measured from the center. Okay. So please compare the two graphs. Sometimes they will look exactly the same, but they're talking about different things. Okay, you need to look at this is y versus t for a particular x position. This is y versus x for a particular time. Any question here? These quantities are related to this graph. These quantities are related to this graph. Okay, in another word, this is if we fix the position and looking at the development of the motion as time change. And this one is we fix the time or freeze it. Okay. So look at different points. What is the motion? Okay. What is the position, oscillation position at a different place? Any question here? The wave itself gives you a very some kind of hint to understand the field. Okay. So it's a quite complicated description. We call it global description. When we're talking about the motion of the particle, this is so-called the localized description, and field is so-called the global description. What's the difference here is that a particle at one time it will occupy only one position. So you only need to focus on that position, right? The particle is here or here. But you see, when we talk about a wave, that's complicated. We're talking about the motion of this point, this point, this point. In fact, when we talk about like an electromagnetic wave, we need to talk about the wave for the whole space. So every place there are something, every position in the space there are something in oscillating. Okay, and they have different phase. Okay, some like here it's in the peak, here is in the valley, here is in between. Okay, so you need, when you try to understand the wave, you have to imagine the motion throughout the whole space. That's global description. It's not just, you're not just focusing on one point here or there. Okay, all of them are an oscillation at the same time. So it's very quite difficult to understand, but in the modern physics, to understand the field and wave is very important. To understand especially for electricity and magnetism, okay, you have to understand this kind of stuff. Okay, now one thing I would like to mention here is that we see that this is describe the repeating pattern for the time. This is describe the repeating pattern for the x for the position. Okay, and when I make this demonstration, you can see that when we show the fast or slow oscillation or crowded or less crowded wave, there are something relationship here. When I try to make fast oscillation, what happens to the distance between peaks? It tends to be more crowded, right? So wavelengths tend to be smaller. When I try to make slow oscillation, can you see that it's less crowded? The wavelengths tend to be larger. Can you see that? It's always so. If I try to oscillate it fast, the wavelength is small. If I try to oscillate it slow, the wavelength is tend to be larger. Okay, so there is some relationship related between the these quantity omega t and k lambda. In fact, they are related by the speed of the wave. Okay? Speed of the wave can be calculated either Okay. Omega over k. That's a fundamental equation. Wave speed equals to omega over k. And since omega equals 2 pi over t, k equals to 2 pi over lambda, you can see omega over k equals to 2 pi over t divided by 2 pi over lambda. So 2 pi, this becomes, so omega over k from the definition is always the same as lambda over t. Okay, so it can also be calculated as lambda over t. Since 1 over t equals to f, frequency, so this can also be written as lambda multiplied by frequency f. Now, you can see how they are related to each other. Usually, the wave speed for any particular system is a constant. It's the property of the system, wave speed. For this system, you have a larger speed. For that system, you have speed, not speed. For example, for the air, the sound wave in the air, the speed we know it's a constant. Okay, it's about 340 meters per second. So that's totally determined by the material, the system, okay, the internal mechanism. You cannot change it by some external controlling. But since it's a ratio of two quantities, you can change one quantity. Then another quantity will change it accordingly. So you can see here, let's check if that makes sense. If I'm trying to make a fast oscillation, okay? So fast oscillation means larger omega, right? Okay. Fast oscillation means large omega. Omega is called the angular frequency, so high frequency oscillation. Now, according to this equation, for a large omega, to keep the same wave speed, what do we know about wavelength k? Should it be large or small? Same V, large omega, should it be large or small? Large. Okay, or you can write omega equals to Vk. So large omega means large k. Now is it correct? Large k means large lambda or small lambda? Large k means small lambda. They are reciprocal with each other up to a constant 2 pi, right? So large omega means small lambda. It's true. Small omega, slow motion, means large k. Okay, less crowded. A small k, large lambda. So large lambda. On the other hand, okay, here, large omega also means small t. Okay, this is fast oscillation. For slow oscillation, you have large t, small omega. Small omega means small k, or no. This is small. Large k means small lambda, and large lambda k. Please note these relationships, they are derived from these equations. So what do we mean by a fast oscillation? It should be small t, large omega, large k, small lambda. Okay, slow oscillation, you have this kind of description. Okay, this is you don't memorize it. I cannot memorize because a lot of. But if you have the formula sheet, you should be able to derive it. Okay, from one quantity, then you get all other quantities. Okay, That's kind of practice for the logic. Okay, I think it's good practice. Okay, so that's a wave. Let's stop here.